last class, I talked to you about the basic hexokinase sensor and glucose oxidase sensor. So, while I concluded the last class, I told you we will talk about this 3 electrode configuration. So, the idea is simple. Idea is whenever we say there is a flow of current, there is a flow of charges, you have to describe it like with reference to what? You have to consider something as 0, which is imaginary. It is almost like we say pH 7 is neutral, where H plus and OH minus ion concentrations are same. So, this is an assumption that this is, we consider 7 as the number out there, and then we move anything lesser than 7, 6, 5, 4, 3, 2, 1 on the acidic side. The other hand 7, 8, 9, 10, 11, 12 alkaline side. Similarly, if this is a reference called 7, in electrochemistry you have to have a reference with respect to that electrode you are measuring. This is an imaginary reference. The very first reference which came historically, all these things started back in the early 1900, 1901, 1902 likewise. First reference which was used was hydrogen electrode, mercury was used and hydrogen electrode was used as the first reference, ready reference. But the problem with hydrogen electrode was or is the complexity of carrying such electrode. From there is a transition which happened, which is called AgCl electrode, silver chloride. So, which was much more easy. These are some of the universal references which are used, depending on, of course, these are all for the aqueous system. There may be other alternative for the non aqueous environment. Okay. Now, with respect to this reference, you have a working electrode and there is a counter electrode. So, the 3 electrode configuration is a very foolproof system, where you are comparing the counter electrode with the reference electrode, working electrode with the reference electrode. Based on that, you are making the calculation. This is to remove all sorts of ambiguity. So, it is a kind of a 3-way thing. W is the working electrode, C is the counter electrode, Re is the reference electrode. Working electrode compared with the reference electrode, counter electrode compared with the reference electrode. That way you are balancing everything, and then the result what you are getting between working electrode and the counter electrode after reducing these differences is the value. And that is why what you see here, we will come back to this 3 electrode configuration later, but at this point, in order to understand why there is an additional reference electrode and what is the difference between the counter electrode and working electrode, this 3 electrode configuration you have to understand in a simplistic term, that this is adding one more layer to ensure that you do not do any ambiguous measurements. Okay. Now, coming back, the tester strip contains the enzyme and an arrangement of 3 electrodes as shown in figure. The working electrode which senses the actual current of the reaction, reference electrode holding a voltage always constant respect to the working electrode to aid with the chemical reaction, and the counter electrode supplying the current to the working electrode. Okay. However, the new designs only need the working electrode and the reference electrode. Also, depending on the model, some devices use glucose oxidase as enzyme, while others use glucose dehydrogenase. This is another new set of information glucose dehydrogenase attached to a coenzyme, pyrroloquinone and quinone, PQ system, and flavin adenine dinucleotide FDA system. Although the inaccuracy and specific issues with GDH and PQQ system due to the main interference with other sugar is known and reported in several setups. So far, the most efficient one is the glucose oxidase system. There are alternative enzymatic system, but they are not as efficient as a glucose oxidase system. Now, if you look at the standard error grid, so when we talk about any sensor, there are standard error grids which are being created. So, for example, what is the risk? So, this is the risk zone. So, A, B, C, D, E. This is like extremely erroneous, dark red. The green is go signal. Okay. A to E. So, clinically correct decision, no effect on clinical action, no risk. As you are going down, it is degrading, clinically uncertain decision, so green and yellow. Okay. Altered clinical action or little or no effect on clinical outcome, mild risk. Now, you are yellow and red, overcorrection that could lead to a poor outcome, altered clinical action likely to affect clinical outcome, moderate risk. So, for every sensor which is being developed, it has to go through a error grid. In this case, this is for the clinical accuracy, the other case is biosensing accuracy, how much you can detect. Unless you have a standard error grid, the industry is not going to accept to develop technology unless they understand that this is the risk they are carrying, because there are other strategic issues involved with it, safety, security, insurance, and there are many other complexities, compliances. So, one has to know in this business how it works. Then it is the red, is it dangerous or failure to detect and treat, altered clinical action, potential significant medical risk, it causes high risk, and the E, which is dark, erroneous treatment. You get a very poor signal, very extreme risk you are playing with, and altered clinical action potential and dangerous consequences. So, these kind of grids are needed for every biosensor which are being developed for sensing a specific kind of biological molecule or biological entity or any toxin or any hormone or any other metabolites. So, you understand when I say in the beginning of the class that opportunity of research and opportunity of job, opportunity of opening industry is exceptionally high, but provided you understand the fundamentals and understand the engineering to develop all these kind of sensors. So, now in terms of the technologies under development for minimally invasive, non-invasive glucose detection. So, this is a chart for MI is minimally invasive, NI is non-invasive. You have optical technologies, you have thermal technologies, you have electric methods, you have nanotechnology methods. So, these are the overall classification of how these technologies are involved. Like you have minimally invasive ultrasound, sonophoresis, we will talk about it, reverse inotropesis. Okay. Then in the electric method, you have amperometry, then you have thermal method, we will talk about that PAS, MHC and thermal spectroscopy. Then you have optical methods, time of flight, this is the mass spec method, FTIR, far infrared, Raman spectroscopy, medium infrared, near infrared, okay, tomography. Then you have fluorescence method, SPR we have talked a little bit, we will talk a little bit in the subsequent class. So, these are the overall. So, whenever you work on any kind of biosensing, this is the spectrum you are looking at, and that is why I told you that this is a vast area of investigation, and one technology has to be corroborated with another technology and when all the technologies for one thing really gives you a clear feeling, then you know the advantage and the corresponding disadvantages of which technology you are free to use. Now, in terms of SPR, we have talked a lot about SPR methods. So, today we will see a direct application. So, this is how the SPR system looks like. Here you have the blood capillary carrying the blood. Here these are the blue ones are the glucose molecule. This is the interstitial fluid here in the skin, and there is a metal electrode on top of your skin of your body surface. Okay. So, now this is made of gold, and there is a prism which is for the detection, and this is the evanescent field. We have already discussed about it, and this is the surface plasmon polaritons. Now, how this is working is as shown in the figure. The basic system followed the Kretschmann configuration, which you have already discussed, consisting of a laser source. Here you have the laser source falling on the surface, monochromatic light, radiating a beam of monochromatic light with transverse magnetic field, also known as P polarization, through a prism. So, it is out here, this monochromatic light is falling on the surface. Under non-resonant condition, the beam is totally reflected when it reaches a prism metal surface without resonating with the free electrons on the metal layer, leaving behind only an evanescent field made of the electrical component perpendicular to the surface. However, under a particular angle of incidence known as the resonance angle theta r, here is that angle, that specific angle what we have been talking about. The momentum of the incoming light equals the momentum of the electromagnetic field perpendicular by the plasma oscillation of the free electrons, causing coupling between the oscillation of the free electron and the evanescent field. Through such coupling, photons are absorbed through the metal layer, causing a sharp, intensely lost dip in the reflected power. As a result, the resonance angle characterized the sample under test given a high dependence on the refractive index of the medium. So, this is where the reflected light, and this is the SPR signal you are obtaining. This is one of the technologies which is of like you do not have to conjugate anything, you do not have to use glucose oxidase or anything, you are just directly putting the sensor on top of your skin and you are measuring it. But this has its own set of interfering molecules and other fine tuning issues which are involved with the SPR. Theoretically, it sounds a really good technique, but then it has its own set of practical issues, and of course, you have to have the instrumentation in place in order to do that. It needs a complex instrumentation process. Now, next technique which I haven't discussed at all is the fluorescence technique. So, what is fluorescence? So, whenever because of irradiation electron emits out from its valence shell and it tries to come back, it travels like this in order to get back to its shell. During that process, it emits a lot of energy. One such energy band is the fluorescent energy band. And we will talk about it, and it comes back slowly. Fluorescence technology is based on the principle of fluorescent light emission at a specific wavelength after absorption of radiation of a different energy level. This is that what I am telling you, absorption energy level causing a wavelength difference known as Stokes shift. The technology makes use of a specialized molecule called fluorophore that emit fluorescent light of a specific characteristic proportional to the concentration of the analyte under examination. This is a very favorite technique, but provided you have a very specific fluorophore which does not offer you noise. In terms of the glucose sensing with fluorescence, In case of glucose, while some of the fluorophores can be bound to the glucose molecule directly, issues associated with the low selectivity, irreversibility and interference and analyte depletion make necessary the use of intermediary molecules called receptors, as they bind to glucose more efficiently and can go through reversible changes in their local properties, leading to altered fluorescence. Furthermore, the receptor can be of different types and nature, including the enzymes, boronic acid derivatives and glucose binding proteins, and even engineered synthetic materials such as carbon nanotubes, quantum dots, allowing the use of several fluorescent techniques and monitoring parameters in a broad spectral range of ultraviolet to near infrared. But still the fluorescence technology is not exceptionally effective for multiple reasons. There is another in that line is called fluorescence resonance energy transfer, or FRET. Among the several existing techniques based on competitive binding assays that has received much attention, as it take advantage of the energy transfer between two sensitive molecules called a donor fluorophore and an acceptor. In principle, when glucose bind to the acceptor molecule, the acceptor donor link is disrupted, leading to decreased energy sharing and increased fluorescence. But in the absence of glucose, the electron transfer between the donor and the acceptor increases, leading to less fluorescence. So, this fluorescence resonance energy transfer is a technique which is a very specific molecular technique, where basically something like this. There are two molecules in close proximity, and what you are tapping is this energy. There is a transfer of electron. In a sense, it is an electron transfer, but in another sense, this technology demands a close proximity of donor and acceptor. This is used in cell biology research extensively. There are people who are trying to use this as a glucose sensing mechanism, but the challenge is, as I was mentioning, of fluorescence is monitoring the fluorescent light can be measured either through intensity or decay time sensing. However, the latter is preferred, which is the decay time sensing, as the fluorescence lifetime is specific to each analyte, permitting the differentiation between substances even if they all emit at precisely the same wavelength. Furthermore, fluorescence lifetime can be precisely measured in scattering media, including skin, indicating that fluorescence technology is suitable for glucose monitoring devices based on transdermal sensing, including contact lenses and disconnected transducer inserted into the tissue, commonly known as subcutaneous implant. Now, in spite of all this, this technology is gaining significance slowly because of several other technological challenges, which I am not discussing here, but it is definitely a worthy candidate for glucose sensing, provided you have a very specific fluorophore binding to glucose. If you could really develop a very specific fluorophore binding to glucose, then you are good to go. Otherwise, the problem is that any fluorophore, if not specific, which has some binding here, they are not kind of, they have other interfering molecules which binds to them, and whenever such thing happens, this whole electron sharing business is getting compromised. So, while it is a great technique, but this needs further refinement in future, and in the next class we will talk about optical polarimetry and other techniques to follow. Thank you.